Matrix representation of two different operators ddx and d2 I asked you to do. No one. Okay. So the morning shows the day. Let's see. So whatever we have shown so far, that you can write any arbitrary function. Say if you have a basis set like phi I, if it is complete means any function can be written as a linear combination of those functions, and if it is orthonormal, that means phi I phi j is Kronecker delta ij, and if I write it in the form of a row matrix like phi as phi 1, phi 2, actually I am writing up to phi n, so that this n means 3n actually, okay. So there are 3n such, or for this it is not 3n, it is any number, whatever we want, we can choose the dimensionality of our problem, okay. But if you go for a specific basis set, for a given system, the number of functions should be automatically taken care of by considering which type of basis. Suppose if you take 6311G for water molecule or for ammonia molecule, so that itself, considering the atoms present, your number of basis functions will be automatically selected. And for orthonormal set, you get phi dagger phi is unit matrix. That means all along the diagonal phi dagger phi you have 1 and all of diagonal elements are 0. Okay. Now, if this is complete, then I know that sum over I Ci phi I. And how do you calculate this Ci? You can see that Ci, if I take this any phi j psi, that would give me immediately sum over I Ci. If I write it, this is a dummy index, remember, Cj phi j. Let me start with this only. So Ci phi I phi j. So I am pre-multiplying by phi j star and then integrating. So this side also all the functions whatever are there in the summation, I am multiplying by phi j star and then integrating. But this one is Kronecker delta ji. That means only when j equal to I, this term will be there, otherwise rest will be 0. That means when this would be 1, j equal to, it would be Cj. So you can see the definition of these coefficients are simply written in this specific type of scalar product. Okay. So these coefficients can be calculated immediately, particularly if it is orthonormal basis. It is very easy to get. Now, actually we talked about the operators and the matrix representation of any operator in a given basis set, how we can write that we have learned. So, in quantum mechanics, you cannot use any arbitrary operator. The operators must be first of all linear, and I have already discussed what exactly do you mean by a linear operator, and also it should be Hermitian. Like if you take any two class Q type functions, say psi and phi, then psi alpha operator phi if this is same as alpha psi phi, remember if it is inside the bra it means it is alpha star. So this integral and this integral, if they are same, we call this alpha operator as Hermitian. Why we require Hermitian operator? So in quantum mechanics you need to have the corresponding operators to be Hermitian, so that there are two properties. One, real eigenvalues, and eigenfunctions. Eigenfunctions are orthogonal to each other. So you can see that if you have a set of eigenfunctions of any Hermitian operator, automatically the corresponding orthonormal basis set you can immediately generate as the set of the eigenfunctions of any Hermitian operator. Okay. Now in this case, so first of all let me tell you about this. I am talking about eigenvalues and eigenfunctions. In fact, suppose if you have alpha operating on psi as some, this is a number, it may be a real number, it may be a complex number. So you can see, I told you that suppose if you operate d dx on sin x, you get a different function, isn't it? You get cos x. But if you operate d2 dx2 on sin x, you get sin x multiplied by some constant, -1 or something. Okay. So the operators which, when suppose if you operate d dx operator, let's say on x square, you get 2x. It's a totally different function. If you operate any operator, so this operator, if it obeys this type of property, this is called a Sharp operator, and this one is its eigenfunction, and this one is its eigenvalue. Suppose if I have d dx e to the power kx, it is k e to the power kx. That means you can see that although sin x is not an eigenfunction of d dx operator, e to the power kx is an eigenfunction of the d dx operator with eigenvalue k. But if you take d2 dx2, sin x is an eigenfunction, e to the power kx is also an eigenfunction. Eigenvalue would be k square, isn't it? So now you understood what exactly do we mean by, say, eigenfunction and the eigenvalue. And if the operator is Hermitian, if you have several such eigenvalues with different eigenfunctions with different eigenvalues or same eigenvalues, if the eigenvalues are different, we call them non-degenerate eigenfunctions. If you have for one eigenvalue only one function, for one eigenvalue if you have more than one function, all those functions we call degenerate functions. Okay. Now a special case of this is your Schrodinger equation. Say h psi as E psi. So here you can see the wave function is an eigenfunction of the Hamiltonian operator with the eigenvalue energy. Now in general, if you want to write, it should be h psi n, E n psi n, because there are several eigenvalues. You see, even for hydrogen atom, you have to know 1s, 2s, 2p, say 3s, 3p, 3d. They are all eigenfunctions of the Hamiltonian operator for hydrogen atom, and we know there is analytical form to find out the corresponding energy. For hydrogen atom, luckily, energy depends only on principal quantum number. So like your 2s and 2p, they will have same energy. 3s, 3p, 3d, they will have same energy. Okay? Because there is no question. So energy eigenvalue doesn't depend on AL or other quantum numbers. So now your job would be, so how to get the matrix representation of this operator, or matrix representation of this operator, let's say Hamiltonian. So I am telling it for a general situation, but remember, at the back of our mind we have this, that we are actually trying to solve Schrodinger equation without solving a differential equation per se. Like if you write Hamiltonian operator, it would be a differential equation, several Laplacians depending on how many electrons you have. And in order not to say make our life complicated, we will go to something else, some other, because we have already developed the acumens, mathematical acumens, in order to solve it in a different fashion. Okay. If you know different mathematical techniques, you can go back and forth from one to the other and solve it. Okay. So now we'll just simply digress and change this whole say analysis of Schrodinger equation. You remember in the postulates of quantum mechanics, I introduced you that is the equation H equal to H, which is to be solved to get the wave function. Once you get the wave function, then you talk about probability of getting a system, you tell it how to get the expectation value of an operator to find out the value what you get. But remember, if you want to talk about the expectation value of the operator, if you take it over its own eigenfunction, you will get the eigenvalue. Remember, say if you put it over here, the expectation value of the Hamiltonian, let's say over psi n, this would be En only, isn't it? Because H psi n is En psi n. En is constant, I can take it out. Then this integral and this integral, anyway they are 1 if they are normalized. So this and this, they will get cancelled and you get only En. Okay, so expectation value will give you always the eigenvalue. So that is the beauty of writing it, that if you do now the measurement also, you will get the eigenvalue. Okay, so in quantum measurements, you will get the eigenvalue of that operator, what you are doing. I am telling it for energy, it is valid for others also. Okay. And that is the reason you get, if you take the eigenfunction as the basis set, if you write the matrix representation, it would be diagonal. And along the diagonal, you will get the eigenvalues. Okay, so that is another check. The eigenvalues you have already checked. Now you see, if they are not eigenfunctions, you have off diagonal elements present. If it is say the set of is of eigenfunctions, then it would be only diagonal, all off diagonal elements would be 0. And along the diagonal, you already know what are the eigenvalues. The eigenvalues would come, that will allow you to check your result, whether your method is right or not. Do you understand? So whatever exercise I have given, say you know what should be the solution. Okay, let me write this. A psi I as lambda I psi I. Okay. So these lambdas are eigenvalues, these are eigenfunctions. Okay. Then this means phi Ci, phi Ci. You see why I am putting I here and not I here? It is just the basis set. It doesn't depend on my function here or the operator here. Only thing is, if you go for different functions, your coefficients will change. That's why I put I over here, not over here. Because the basis set is independently coming from somewhere else. Okay. Now, this, as operator is not going to change this one, operator I am putting it over here. So now you can see, so this part is same. I can write, or I'll do something more intelligent. I again pre-multiply by phi dagger. Here also I pre-multiply by phi dagger. Okay. So previous expression, I am pre-multiplying by phi dagger. So this phi dagger, phi dagger, this is unit matrix. Okay, that is multiplication by 1 just. So what I get is ACI is lambda I Ci. So you can see sorry, no, this operator I cannot take it out. This operator, it should operate on these functions, that I cannot take it out. Sorry. This I cannot take it out. So, because these are functions, I cannot take it inside. So, phi dagger, this A phi, phi dagger A phi. What is phi dagger A phi? That we have already checked. This is the matrix representation of the operator A, isn't it? That we have already checked in the last class. So, your ACI is lambda ICI. Okay. Perfect. So this is actually, we call this as the matrix eigenvalue problem. And here your I is 1, 2 up to n. There are separate equations for each I. Okay. Separate equations for each I. And this equation we'll call matrix eigenvalue eigenvector equation. So now here you can see this one was in the operator form, like the Schrodinger equation, the way it comes. So this one, if you consider A to be Hamiltonian, lambda is energy values, EIs, then your A is a, let's say, second order differential operator. Maybe there are several Laplacians are added. And this equation we call this an operator equation, differential equation. For Hartree-Fock equation it would be integral differential equation. For Kohn-Sum equation it would be integral differential equation. They are integral operators, differential operators both. And this function we call eigenfunction, this number we call eigenvalue. Go back to this. This one is just the matrix equivalent of that, because this is your matrix representation of that operator A and in your chosen basis. This is your eigenvector, this is your eigenvalue. So which was eigenfunction eigenvalue relation, that has become eigenvector eigenvalue relation. That means the role of this matrix, this operator turned out converted to a matrix, is to convert your vector, eigenvector, to a collinear vector, because it's just a numerical factor of length lambda I Ci. Perfect. Here also, suppose if you can solve this equation, you get eigenvalues like energies, you get the wave functions also. Here if I solve, I get the eigenvalues, means energies for Schrodinger equation. Also the eigenvectors I will get if I can solve this matrix equation. Once I get the eigenvectors, I know my basis set which I have chosen. Simply I multiply, I get the wave function. Okay. The psi is a phi matrix into C matrix. So if I solve this, I get C matrix. Also I get lambda I. Now technically, what is this gist or a compact form of, it's a compact form of a set of n linear simultaneous equations. Okay, so I am talking about a set of n linear simultaneous equations. Actually, I was writing capital N linear simultaneous equation. Do you know what are linear simultaneous equations? No. Suppose if I give you two equations, a1x plus b1y is c1 and a2x plus b2y equal to c2. Two equations, two unknowns x and y. Okay.
One service will be there so that both equations will solve. Both equations will
Your job would be to find out what is x, what is y, so that they will satisfy these two equations. They are called linear equations, as only operation is here is addition and scalar multiplication, that's why they are linear equations. And simultaneous equations means if you want to get x and y, those values will simultaneously satisfy these two equations. I hope this class 5 level problem, you would be able to solve these two equations to get x and y, isn't it? If it is 2 by 2, no problem. Even 3 by 3, 4 by 4, Cramer's rule is there. You know, you have to learn a little bit of determinant. But anyway, that you have learned already, isn't it? So now we will see that we had a very complicated differential equation. We have come back to a set of linear simultaneous equations. So we will see how do you get them. Say if I write A matrix is your A11 first row, second column, first row, first column, first row, second column. This is your A matrix. Okay. You see, when I write the matrix element, the first index is for the row and second index is for the column. So that way you can write immediately. So this is element for the first row and second column. That's why I want to. Similarly, Aij, and we know the definition, how to calculate all these matrix elements, that we know, isn't it? That's the matrix element of so the operator A within the basis functions phi I and phi j. That would give you Aij. Okay. Then you have if you expand this, can you tell what will you get? So this is your ACI equal to lambda ICI. I have written it like this, isn't it? The same equation where explicitly the matrices are written. If you expand this, what do you get? You get A11 C1 plus A12 C2 plus A13 C3 A1n Cn is lambda I C1. This equation 1. A21 C1 plus A22 C2 up to A2n Cn, this is lambda I C2, equation 2. This way all the way up to An1 C1 plus An2 C2 An Cn Cn. So this is your nth equation. So you can see these are n linear simultaneous equations. They are, I had written explicitly for two variables x, y. Here you have unknowns C1, C2, C3 up to Cn, n number of unknowns, n number of equations. All these A, etc. known to us because we know Hamiltonian, we know our basis set. We can calculate them exactly. Only thing, so what we don't know, C's. So there are n number of unknowns and n number of equations. But is it true? There are n number of unknowns. Actually, these lambdas are also, lambda I is also not known. That means, say you have n plus 1 number of unknowns and n number of equations. Actually, when you solve the Schrodinger equation as such, they are also, not only the wave function is not known, energy is also not known. You have to solve the equation to get both of them. Okay. So here we will take a special care to do this. So if I take this, all of them towards left, then you can see this lambda I C1, I can subtract it from here. So A11 minus lambda I into C1. This one will come here, A22 minus lambda I into C2. So all along the diagonal, your lambda I would get subtracted. So this would be, it's not 0 because it's a matrix, it would be a null matrix. All elements are 0. That means it's just a null matrix. Okay. So this is the situation. So in matrix form, it is this. Okay. But lambda I cannot subtract this like this, so I multiply this by unit matrix, because I have to subtract lambda I only from the diagonal. You see, if I multiply lambda I with the unit matrix, so this lambda I into 1 will have only along the diagonal lambda i's, and rest of diagonal elements should be 0. So if I subtract this, I will get this one, isn't it? Try to understand. You can try. You write the identity matrix 1 or unit matrix, which is 1 all along the diagonal and all off diagonal elements are 0. Multiply that with lambda I. So lambda I will come all along the diagonal. And now if I subtract, I will get only this. So lambda I will not get subtracted from all elements. It will get subtracted only from the diagonal elements. Okay. So this is a very simple trick we can take. Okay. So now I will tell you certain techniques for the solution of this type of equations. So these are known standard, say, techniques in linear algebra, how to solve this type of equation. So these are again your matrix equations, how to solve them. So the first thing is a product of two matrices, A minus lambda I into 1, this one matrix, and Ci is another matrix. And the product is a null matrix. So trivial solution, obviously, trivial solution is Ci is your null matrix. So if I have all Ci is null matrix, then obviously this should be satisfied. Multiply anything by 0, that will be 0. Okay. But you know, if your Ci is 0, your wave function becomes 0, because Ci into basis set phi matrix is the wave function. So you don't want that. You don't want to get the 0 value of the wave function. So you want a non-trivial solution. So non-trivial solution is that, by the way, those equations what I had written here, they are called secular equations. So this is the term you will hear in quantum chemistry. So they are called secular equations. Secular has the similar meaning as we know in current day, politically secular, so religiously secular. So these are the same meaning as secular, because there we are not assigning any specific condition. So those linear simultaneous equations, they will be satisfied whenever, say, all the unknowns, they are plugged in. You may have your own solution, I may have my own solution. So, but you have to make sure that all of them are getting satisfied. That's why they are secular equations. Now, non-trivial solution is the determinant of this must be, so it would be a singular. That means the determinant, this is called a singular matrix. So the determinant must be 0. And this determinant is called a secular determinant. What's the time? 10:40. Okay. So maybe I will take another 10-15 minutes. So this is your secular determinant. So lambda is subtracted from the diagonal and other elements are there, and we know all the elements. We don't know lambda is, and this is not null matrix. Remember, determinant is a number, so it's 0, simple 0. Okay. Now, as you can see that if you expand this determinant, do you know how to expand a determinant? Yes or no? So if you expand this determinant, so lambda is there in all rows, it is coming once. So, and all others are, say, known values, all matrix elements. So it would be a simple polynomial of degree n in lambda. That means it would be something like lambda I to the power n plus alpha 1, lambda I to the power n minus 1 plus alpha 1, alpha 2, lambda I to the power n minus 2 plus alpha n minus 1, lambda I plus alpha n, and this should be 0. So this is a polynomial equation in lambda, nth degree polynomial. Okay. Now if I solve this equation, so suppose if your n equal to 2, you get a quadratic equation, x square plus bx plus c equal to 0. If you solve that, what do you get? You get 2 roots. So it will have n roots. Okay. So n roots, if I give this name lambda 1, lambda 2, etc. up to lambda n, this one will call eigenvalue spectrum of this matrix A. If you solve the Schrodinger equation also, you will get eigenvalue spectrum of the Hamiltonian operator. There you get in the form of operator, you get all solutions. So if you solve particle in a box or harmonic oscillator, you get analytical forms for those eigenvalues. Okay. But here if you solve the matrix equation, you get the corresponding eigenvalue spectrum. After that, how will you get, once you have this eigenvalue spectrum, you remember, if you go for each, and some of these eigenvalues may be same also, then we get the degenerate set of corresponding eigenvectors. Okay, like there you get say 1 s orbital, 3p orbital, 5d orbital. For one electron problem, you have additional, say like 2s and 2p. Orbital wise, they are all different, but same energy. 3s, 3p, 3d, all of them are having same energy. For all one electron problem, hydrogen, helium plus, lithium 2 plus, they are all called hydrogenic systems. All hydrogenic systems, it depends only on the principal quantum number. Okay. So now, for each eigenvalue, you must have one separate eigenvector. You don't have the same eigenvector. So you have to solve that equation now. Your original equation, you remember, the equation is This is the equation. Now, if I put this lambda now in the matrix form, I will get separate lambdas and separate CIs. So now instead of this, say CI is, I will put for each lambda I will say this one is my CI. But this CI now will have elements C1i, C2i, Cni like this. Okay. So now you can see that I am trying to put again all of them back in the similar framework. So I will get, say for lambda 1, lambda 2, I will get C1, C2, C3 up to Cn. And if I put all of them over here and I call this, let's say, as C. Okay. So this is for one lambda, this is for another lambda, this is for another lambda, and so on. So this one will have C11, C21, Cn1. The one have C12, C22 up to Cn2. Okay. So I can get it. And lambda, I put it along the diagonal, this one. So I will get lambda 1, lambda 2 up to lambda n. And here you have a 0, here you have a 0. All of diagonal elements are 0. Okay. Perfect. So what you get here, AC should be your C lambda. So you can see now I am clubbing all of them over here. All possible eigenvalues are coming along this diagonal, and for each eigenvalue the corresponding eigenvectors are given in this form. Okay. So this is very important expression. So this is the general form for your matrix eigenvalue eigenvector equation now. And this lambda, say we got after the solution of the simultaneous equations. And once I get this lambda, then my job would be to find out the eigenvectors. Now, suppose if C is a non-singular matrix, I can find out the inverse of that matrix. Do you know by any chance how to find out the inverse of a matrix? Yes or no? No. Okay. So if I multiply this, let's say C inverse AC this one is unit matrix. That means this should be okay. Actually, in a general situation, this should be C dagger. Okay, but for let's say unitary matrices, C dagger matrix is same as C inverse matrix. So I have written C inverse. So if I write like C inverse AC, this process in group theory you will learn in many places. This is called similarity transformation. Okay, this is what we call similarity transformation. So this is the diagonal matrix. This one is your original matrix. Suppose if this is your Hamiltonian matrix, this is your eigenvalue matrix. Okay, the energy value like energy matrix. All along the diagonal you have the energy values. So this process is called diagonalization of a matrix. So that is what in quantum chemistry your package is doing, you may not know, is diagonalization of matrix to get the eigenvalues. Okay. So once you fix the basis set and a system, so the system will specify immediately the Hamiltonian operator, basis set will tell you immediately the basis function, they will immediately construct the operator form of the Hamiltonian, and then get the way I have shown you the eigenvalues. Once you get the eigenvalues, actually your problem is solved. But no, the simplest possible thing, numerically what they do, it is not analytical, numerically they do, but you can do it analytically if you have a simple problem. Your C inverse AC, that means a similarity transformation here can give you a diagonal matrix, and this is called the diagonalization process of your matrix A to get the eigenvalues. For quantum chemistry, that would be your energy eigenvalues. Okay. One important thing what you can see, that for any matrix can be diagonalized through a similarity transformation by its own eigenvector matrix. Okay, that's a very important theorem, that any matrix can be diagonalized through a similarity transformation through using its own eigenvector matrix. Okay. Now suppose if you know the eigenvector matrix to start with, obviously you have solved already the problem. So how will you do it? So numerically, you do what a process is called Gaussian elimination. I don't know whether, have you ever, any one of you heard this name, Gaussian elimination? This is a numerical technique. So what is the Gaussian elimination? What will it do? So you start with some arbitrary matrix C, get its inverse or adjoint depending on what type of problem you are handling. Your A matrix is already known. You do the similarity transformation like this, C inverse A C. But it is not C, it is your arbitrary matrix you have started with. Check the fate of this one. Obviously, to start with, you won't get a diagonal matrix. You will get several off diagonal elements. Now, there are techniques to reduce the values of the off diagonal elements and to pump in the similar values or transfer the similar values towards the diagonal. Okay. You have to identify certain pivotal elements, and then you have to do some standard operations are there. If someone has learned anything about computer programming, I think this is, they must have learned it. I think Tumpa must have learned it. No, you have forgotten. Huh? Yeah, but you learned some time back. So this is something what you can do. You iteratively now keep on doing it, improve your this matrix, looking at the behavior of this matrix. And when it may not be exactly diagonal, depending on your computer problem, computer power, depending on your requirement, you may tell that if it is like 10 to the power minus 4 and less than that, I will consider mod, of course. If it is negative, always it will be less. So 10 to the power minus 4, then I will consider that to be 0. And then that so-called diagonal matrix. Which matrix could give me that diagonal matrix? That will be my eigenvector matrix. So if I get the eigenvector matrix, I have actually solved my problem. Because I know my basis function matrix, multiply it, I get the wave functions. Lambda I have already obtained, because along the diagonal of this matrix, whatever just now we have obtained, I have my energy eigenvalues. So I got energy eigenvalues, I got the wave functions. Period. Okay, stop. Guarantee. So you tell if you have any query, you could not understand anything anywhere, whatever I told. Okay. And another thing, consider a specific matrix. Let's say it may be Hamiltonian also. No, for simplicity, I am giving you only a 2 by 2 matrix. So you try to solve that matrix. So A is, let's say 7 minus 3 root 3 minus 3 root 3, 13. So this is a simple 2 by 2 matrix. If you solve explicitly a matrix eigenvalue eigenvector equation, then you will learn the technique very well. Okay. So remember the steps. What you have to do. So here you don't know the eigenvectors, you don't know the eigenvalues. Okay. So if this is your A matrix, basically you have A Ci is lambda I Ci. So this is your matrix. So you have to find out for this A matrix Ci's and lambdas. So what is to be done? You have to construct the secular determinant. So secular determinant you construct 7 minus lambda minus 3 root 3 minus 3 root 3, 13. This is your secular determinant, 13 minus lambda. This is your secular determinant. Perfect. And this is for non-trivial solution, this must be 0. So this is a quadratic equation. Can you immediately tell what are the values of lambda? How to get this determinant? This into this minus this into this. Okay. So you get a quadratic equation. What is the quadratic equation are you getting? What?
Lambda square minus 20 lambda plus 64.
So lambda square minus 20 lambda plus 64 equal to 0. So lambda, you have two values. What are the two values? It's a very simple. 20 is 4 plus 16 and 64 is 4 into 16. So this is again class 5-6 level problem. So you do the middle term and get the solution. So what are the lambda values? 4 and 16. Okay. So lambda 4 and lambda 16. So general secular equation should be 7 minus lambda I C1I, what was there? Minus 3 root 3. Minus 3 root 3 C2I equal to 0 and 3 root 3 C1I plus 13 minus lambda I C2I equal to 0. So this is 1. So this I will tell you that there are two values of lambda. So it would be C11, C21 and C12, C22. Okay. So these are the two equations which are to be solved. So first, if I call this is my C1 matrix for lambda equal to 4, that would be C11, C21, and for lambda equal to 16, you have the C2, that would be C12, C22. Okay, perfect. One I, two I. I1 means lambda equal to 4. I2 means lambda equal to 16. Okay, perfect. And what is your, this also I am writing here, what is your lambda? This is 4, 0, 0, 16. This is your diagonal eigenvalue matrix, isn't it? So here, first you put lambda I is lambda 1 as 4. Here you write C11, C21. Here you write C11, C21, lambda I equal to 4. Solve that equation. So that would be eigenvector for lambda equal to 4. Then you solve it for lambda equal to 16. Do it. Again, two equations, two unknowns, linear equations, no trouble. If I give a 3 by 3 matrix, there also you can apply Cramer's rule. If I give a 4 by 4, you can do it, say Cardan's method or typical analytical solution, or actually you can do again using Cramer's rule with a 4 by 4 determinant. Okay, no problem. Are you facing any trouble? You see, you will face a trouble. Why? The two equations are linearly dependent. Basically, you are getting the same equation. I don't know whether you could reach to that point or not. These two equations, basically, they are not different equations. You are getting the same equation. Isn't it? You are getting same equation. So, but there is, you know, if it is a Hermitian matrix, its eigen function should be orthonormal. If the eigen functions are orthonormal, then you get a condition that C1I square plus C2I square must be 1. Okay. So you simply write psi as say C11 phi 1 plus C12 phi 2, and then put psi star psi dx integral equal to 1. That will immediately give you this condition. Okay. So you put, so this is another condition. So this is equation 3. So now you would be able to solve. You will get 4 values: C11, C12, C21, C22. Okay. 2 for lambda equal to 4, 2 for lambda equal to 16. It's a 2 by 2 equation, so you must be able to solve. So what are the values? And here, after you get this, your C matrix would be C1, C2. Okay. So could you get this C1 matrix and C2 matrix? You see what you have to do, you write C1I in terms of C2I, C11 in terms of C21, and then put it over there. That will solve your problem, isn't it? So this means what? C11 square plus C21 square equal to 1, and C12 square plus C22 square equal to 1. So for one case you do this, and for another case you do that. So shall I have to tell also that 7 minus 4 equal to 3? So that you would be able to do. So do it. Hey, 2 by 2 equation you cannot solve. What is this? You are getting same equations. Can you follow at least what I am writing? If you cannot do it yourself. Now this one, you put it in this C11 square plus C21 square equal to 1. For C11 you put this. So what do you get? 3 C21 square plus C21 square. So C21 square, 4 C21 square. C21 square is 1/4. So that means C21 plus minus half, you take just half. So C21 is half. If C21 is half, C1 is root 3 by 2. Okay. C21 is half. So C11 root 3 times that is root 3 by 2. What happened? You will be doing quantum chemistry. So this is class 5 level problem. So can you do it? So now you got it. C11, C21. So you get C11 as root 3 by 2 and C21 as half. Okay? I think still I can see some faces. Maybe you didn't understand what is done. Yes or no? Louder. Understood. Correct? Do it for lambda equal to 16. Same process for lambda equal to 16, only for 1 1 you have 1 2 and 2 1 you have to do 2 2, because lambda 2 you are doing now. Okay? And in that case you have to take another equation, C12 square plus C22 square equal to 1. Okay? Do it. What happened? Tell. So what is your C matrix now? C1, C2. So your C12, C11, C21, root 3 by 2 half. Root 3 by 2 and half. What are the other two? Hello?